Okay, we are on chapter 10, which was talking about obviously energy in this chapter. And last time we talked about some important sort of units of energy. The two probably most common ones we'll come across is joules or kilojoules. And the relationship there is 1,000 joules equals 1 kilojoule. There's also calories with a little c. Are kilocalories, and kind of the same conversion there. 1,000 of the little calories there is 1 kilocalorie. The relationship between sort of joules and calories is a calorie is 4.184 joules, so that's a nice relationship. We talked about a couple of types of processes, including exothermic processes. Exothermic process, as we talked about, is when heat or energy is released. And as we talked about last time, we'll see more today. Usually that will result in sort of a negative value for that system or whatever may be releasing the energy. If you were to sort of calculate an energy value, typically that's a negative value. Endothermic, on the other hand, again, is when heat and energy is absorbed. And unlike sort of exothermic there, typically when you calculate an endothermic sort of energy value, it typically is going to be a positive value. So one of the things we talked about is the law of conservation of energy, which is really also known as the first law of thermodynamics. And that states that energy cannot be created nor destroyed. So there's this conservation. So as I mentioned last time, we sort of think of energy as this sort of flow, kind of perfect flow, if you will, from one spot to the next. So in a lot of our sort of situations, if somebody gives away a certain amount of energy, something else will gain that exact same amount of energy. It's just going to be exothermic for one and endothermic for the other. Um, we also talked about state functions. State functions are things that really don't matter how you get there, or the pathway, but the really only two things that truly sort of matter is sort of where you started and where you ended up at. And that, as we talked about, relates to chemical reactions. And again, we have our reactants, which is our starting material in a chemical reaction, and they go to products. And that's obviously what is formed as a result of a chemical reaction. And a lot of ways that we calculate sort of energy and a lot of things is to take sort of our final state minus our initial state. So when we talk about sort of chemical reactions, our final state is typically our products that were formed. Our initial state is typically our reactants. So one of the ways that we could calculate energy for a reaction is to basically add up all the energy sort of associated with the products, bless you, and it's kind of subtracted from all the energy associated with the reactants. And that difference is sort of either going to be the energy absorbed or released by a particular reaction. Any questions on any of that stuff there? Yeah. All right, so sort of picking up. Let's talk a little bit about thermal energy. Thermal energy is the energy that's associated with the random motion of atoms or molecules. The more vigorous the motion of the atoms or molecules, the hotter the sample will get. Remember that we sort of talked about temperature last time, and we'll talk a little bit about it here again. Remember, sort of a temperature is sort of a reflection of what is happening in terms of energy flow. So again, if somebody does gain energy, typically speaking, the reflection of that can be seen in temperature. We would typically expect their temperature to increase as they are increasing the energy and absorbing that energy. And vice versa, if somebody is sort of releasing energy, the reflection in terms of temperature is we typically will see their temperature decrease from where they started with as they sort of release that energy out. And there is a difference between thermal energy and temperature. So, for example, if you had a cup of coffee at 70 degrees Celsius, and you had a bathtub at 40 degrees Celsius. In terms of thermal energy, there is definitely a lot more thermal energy in the bathtub, even though it has a lower temperature, because clearly there is a lot more molecules of, say, water in the bathtub than there is obviously in your cup of coffee. Why is the temperature different? Has something to do, we'll talk about later on in the chapter as well. But for example, the amount of water molecules there are in that bathtub will take a lot of energy to see a very big change in the temperature, as opposed to if you have just a cup of coffee, there's not a tremendous amount of water molecules in there, so it may not take as much energy to see a greater amount of temperature change. So you think about if you boil a very small amount of water, it tends to boil really quickly, right? If you got a giant pot of water, you got to wait for a while for it, just because of the volume of water that's present. So because the amount of energy needed to raise 1 degree Celsius of this much water, um, and because you have so much of it, it's going to take a lot more energy to see a bigger temperature change than here, where you have a much smaller amount of water present. So, because thermal energy is related to number of molecules, the bathtub definitely would have a lot more thermal energy. So heat, as we've been talking about, again, is the flow of energy due to a temperature difference. And as we talked about last time, a reminder that heat does flow from hot to cold. So the hotter object will get colder as it releases that energy. The sort of colder object will get warmer, if you will, because it's picking up that energy. And again, when we talk about, for example, if you took a hot piece of metal and you put it into some room temperature water, the hot piece of metal is obviously higher in temperature than the room temperature water. Energy would transfer from the metal to the water. So again, if you had some water at room temperature, and you heated up this hot piece of metal and you put it in there, when it goes in there, for the metal, it will really be a exothermic process. It's going to release all that energy again to the colder room temperature water. For the water, it is endothermic, and that's usually two things that oftentimes happen together. Again, because if somebody is having an exothermic sort of situation happening, that means it has to release that energy and somebody else has to absorb that energy. So it's always really important when we talk about energy, or even maybe do calculations involving energy, that we think about sort of that flow of heat and energy, and who is kind of the exothermic sort of part of it and who is the endothermic. Again, exothermic is the process that gives off heat and energy to the surroundings. If you light a Bunsen burner, strike a match, again, you can kind of put your hand near it and you can feel the heat coming off to the surroundings. And it's exothermic once again for the, say, Bunsen burner or the match. It is endothermic for the surroundings, which is picking up that energy. Or if you put your hand near it, your hand's going to pick up that energy, right? It's going to get really hot quick because your hand's absorbing all that energy, right? And that's why the hand gets really hot. We also, I think, talked about last time, just that is why as well, right? When you take out a piece of ice from the freezer, it is much colder than the room temperature, so the flow of energy is actually going into the ice, and that's why it just starts to melt. You don't really have to do much to it, right? It's just going to start to melt because of that flow of energy from the surrounding air, even though it doesn't feel cold to you or warm to you. It is much warmer than the ice, so that flow of energy is going to go into the ice cube and help it start to melt. Let's talk a little bit about these sort of pictures here. These pictures here are what are referred to as energy diagrams. And these are energy diagrams for both of those sort of processes, a endothermic process and an exothermic process. And let's take a look at sort of what is happening here. So first off, we do have, we'll just redraw one here a little bit here on this page. And we'll do something like this. All right, so this is obviously energy. This is obviously the reaction is progressing in this direction. So remember that we do have reactants going to products. So this is the energy of our reactants, and I'll just call it R here. And here's our energy of our products. And one of the first things that we see and can recognize from this type of graph is this is a exothermic process. And that is because our reactants or our starting material is higher in energy than our products. So the only way for those guys to kind of get down there in terms of energy is energy has to be given off to allow those reactants basically to get down to those products. So whenever you see an energy diagram where the reactants or the starting material are higher than the products in terms of energy, that is always an exothermic situation. That's always going to kind of net release energy in this process. Now, what happens in a chemical reaction as we go from reactants to products is basically pretty straightforward. We basically break all these bonds. So all the bonds of the reactant molecules, whatever they may be, we basically just break apart all those bonds. And then on the product side, we actually just make new bonds. There is conservation of elements. We do not lose elements along the way. So if we started with 6 carbons on the reactant side, we will end with 6 carbons on the product side. They may be in different things, but we won't lose any elements. So we always have the conservation of elements when we do a chemical reaction. So what happens as this is happening? Well, in order for a reaction to occur, there's actually 2 things that actually has to happen. They actually have to come in collisions with each other, so they do have to collide with one another, reactant molecules. So if you have like A and B, these 2 guys basically got to run into each other to start a reaction. Now, just because they run into each other does not mean that you actually make products. They actually have to hit each other in the right location, almost like an active spot there. They actually have to hit each other in the right location. The other really important thing that they need to do is hit each other with the right amount of energy to let this reaction take place. And that right amount of energy is this heel that we see here in this picture. And this heel, in terms of energy, from where the reactants start to the really top of energy part of the reaction, this is known as the activation energy. And the activation energy is sometimes abbreviated as E of A, and that is the minimum amount of energy needed for a reaction to occur. So this hill that these reactants has to climb is the energy sort of barrier basically to get to the other side. Now, what happens is once they kind of get to the top there, they do kind of drop down to the other side relatively quickly. But that energy hill or activation energy plays a very big role in how fast or slow a reaction would take place. So, for example, if I had a really big activation energy hill, that's probably going to result in a much slower reaction than if the activation energy hill was much smaller. Like if you were walking, you had a giant hill to get to the other side of campus. It's going to take you a lot longer to get up and over that hill than if you just had like a little bump or speed bump, right, to get to the other side. You're going to definitely get over much quicker. And that also is what's happening here with this activation energy. Now, one of the things in chemistry that you should know is if we look here at the very, very top of that energy hill, this is what is sometimes referred to as the transition state. And at the transition state, you have a complex, which is sometimes referred to, I go over here, as the transition state complex. Some people call it the activated complex. But what you have at this very, very peak of energy is kind of like an intermediate. So In order for our reactants to make our products, they got to start breaking bonds. They also have to start making bonds. And that is what's happening as this guy basically starts to climb this hill. We're going to start breaking bonds and we're going to start making bonds. So as it's coming up here, it will start to break bonds and make bonds. And what happens is when it gets to the very top of the hill, you have this transition state complex which has partially broken bonds and partially made bonds. So this kind of intermediate type of guy between the reactants and the products, where it's in the process of breaking all those bonds, but also in the process of making all the new bonds that has to happen before it gets to the product side. And this happens at the very top here. That is our transition state. That's the highest point in energy. And in chemistry, things in high energy states are not very stable. Things do not want to be in high energy. It's like the worst situation. Pretty much everything that happens in chemistry is in an effort, in a lot of cases, to lower the overall energy to a lower energy state, a more stable state. So this transition state complex, which you find way up here, is very, very unstable. And like I said before, it doesn't really hang around a long time because of that, because it's got like partially made bonds, partially broken bonds, and it will very quickly drop to the other side and make our products in this case. Any questions on that there? Now, this is a exothermic reaction. An endothermic reaction will look very similar diagram, but there are a few differences which are important to note. This will be our reactants, this will be our products. This is again our energy. And again, our reaction is just happening going in this direction with time. This is a endothermic reaction where energy is being absorbed. And I know that because my reactants are lower in energy than my products, which essentially means I got to put energy in to do this. Energy has to be absorbed to do this. And whenever we have reactants lower in energy than products, it's going to be an endothermic reaction. We have the same sort of parts from the reactant energy to the very top of our hill. That again is our activation energy. This is our transition state at the very top of the hill. By the way, which one has a bigger activation energy hill? Yeah, the endothermic versus the exothermic. And that is typically the case as well. So if you just think about that, endothermic means it needs to kind of absorb energy. So it's got to gain some energy to come up and over that bigger hill. Got a lot of energy, so not a big issue. And usually we'll have a smaller hill. Same thing is happening here as we come up the hill. We're breaking bonds and we're making bonds. And just like last time when it hits this transition state, it will drop down to the other side relatively quickly as well. So whenever you see an energy diagram where you have reactants lower in energy than products, it should be an endothermic situation basically happening. One of the ways that we look at energy in a chemical reaction, as we'll talk about here in a second, is what's known as delta H of the reaction. And this is what is known as the change in enthalpy. And it's a fancy way of saying basically how much energy is either given off in a reaction or absorbed in a reaction is basically what that is. One of the ways that we calculate delta H for a reaction, because it's a state function, is we basically take the delta H of all of our products, so all of the product energy, minus the delta H of all of our reactants. So we take our, again, final state minus our initial state, products being our final state, reactants being our initial state. And when we look at just the difference here in this graph, if you take the energy difference between where the reactants are and the products are, that is your delta H of your reaction. So if you take the energy difference between the reactants and the products. That will give you your delta H. So if I were to calculate this, delta H for this example in my picture here, although I don't know the numbers, I do know that I'm going to take the delta H of my products, which is lower in energy, so I'm going to take a smaller number, minus the reactants, which is higher in energy, which would be a larger number, and that's going to yield me a delta H that's going to be a negative number, as we talked about before. So again, energy values that end up negative is a result of an exothermic process, and that's what's going to happen when you do that calculation. If you actually had numbers and put them in there, you would end up with a negative value. Just for example, obviously this is lower, so say that's 2, say that's 4, not obviously the right numbers. So if I took 2 minus 4, negative 2, negative value here for my energy. And again, that is going to happen because of where the reactants are starting in energy and the products are ending in energy. So that difference between those two. Any questions on that there? Now, if we look at our endothermic one, we take the energy difference between the reactants and a very badly straight line drawn there. And if we take that energy difference between our products and our reactants, that again is going to give us our delta H of our reaction. And if we take our delta H of our reaction, again, the delta H of our products minus the delta H of our reactants. And here we see our products are actually higher in energy. So this will give us a larger number. And reactants are lower in energy, minus a smaller number will give us a positive value for our delta H. Again, if you just want to put fake numbers in, 2 and like up here would be 4. In this case, we would do delta H is 4 minus 2, positive 2, right? So a positive number here telling us it's going to be endothermic in this reaction. So delta H is probably, I would say, in your chemistry career, the most common way that you will know whether or not, for example, a reaction is endothermic or exothermic, either by calculating the delta H, which we'll talk about how to do that here in just a second, or if you're given a reaction, very commonly the way they tell you basically it's an endothermic or exothermic reaction is they will give you the equation, and at the end of it, they'll just write delta H is either a negative number or a positive number. The number really doesn't matter in this situation. It's actually the sign that's really important here. And again, if you see a negative sign, you could automatically know that process is going to release energy. It's going to be exothermic. If you see a positive value, you know it's going to be a more endothermic sort of process. This is also why, as we talked about last time, it's really important when you are calculating energy values that if you do end up with a negative number, you keep it in terms of energy because it does display whether or not that reaction is exothermic or not. If you just write the positive value, you're kind of saying that it's an endothermic reaction when perhaps it's actually an exothermic reaction. So the sign is really, really important, positive or negative, when we're dealing with energy values. Any questions on that there? All right. So here we can see these are our reactants going to our products. Just another sort of way energy is sort of displayed here. We can see our reactants are higher in energy than our products. Energy is going to be given off, so once again, exothermic. Here, this is our reactants down here going to our products. So our reactants are lower in energy than our products. Energy has to be absorbed in this case, once again, becoming an endothermic situation. So to sort of summarize what we've been talking about, again, exothermic energy release. When you look at a chemical reaction or equation, sometimes people actually put energy sort of into the equation, either on the reactant side or the product side. Not too much in these classes that you take, but sometimes you do see it. So for example, here, if we look at this combustion reaction, we see we're getting 213 kilocalories of heat being released. This is on the product side, which means that this is going to be exothermic, like it is being given off as a result of this reaction. You're kind of releasing that much energy. Here we see 12 kilocalories of energy or heat being on the reactant side. And that tells us it's like it's being gained into this reaction and absorbed, and that would be an endothermic reaction. So if you actually see heat and energy written in the equation, I'll be honest with you, I don't know if you'll see too much of that in these classes here. But if you see it on the product side, it tells you it's exothermic, or if you see it on the reactant side, it is endothermic. A place where this does come in handy is understanding that concept. For example, in a couple classes down the road there, you'll talk about what's known as the Chatelier's principle. And when we do have an exothermic reaction, we think of heat and energy as almost just being a product, an additional product. And when we have an endothermic reaction, we sort of consider it, although it's not probably correct in all aspects, we consider it as being a reactant, another reactant. I would say, like I said before, most likely, if you had an equation, you probably want to see it actually written in. What you would see at the end, delta H is a negative value, and here you probably want to see it written in. Delta H is a positive value, and again, that's probably the most common way that you will see sort of exothermic and endothermic displayed in chemical equations. Any questions on that? So as we talked about, heat flows from hot to cold. So if you had some water at different temperatures in an insulated box, all the energy here is going to flow from the hot to the cold there. That's going to cool down the hot water side temperature. It's going to raise the temperature of the cold side there as it's gaining that energy. And since this is a nice insulated container, they probably will meet somewhere in between. So as it sort of increases energy on the right, decreases energy on the left, they'll probably bottom out somewhere and come to equilibrium with each other and sort of be at the same temperature in this case, maybe 50 degrees on each side. So let's talk a little bit more about enthalpy and sort of how we calculate it. So as I mentioned before, most common way we represent energy in chemical reactions is with the enthalpy. And again, the abbreviation for that is H. And most of the time it is delta H, which, as I wrote on the last slide there, is the change in enthalpy. And we calculate it basically by taking the delta H of the reaction. You add up all the delta H of your products minus the delta H of your reactants. And as I mentioned, and what you just talked about, if you do end up with a positive value, that will tell you it's an endothermic process. And if you end up with a negative value, it'll be an exothermic. Now, there's a couple of things that are important when you do this. Let's just say, for example, we have this reaction here, 2A plus B goes to 3. We'll do C. Now, where do you find these values of delta H for, say, your products or your reactants? You actually, in most cases, find it in a table. So there's what's known as a thermodynamic value table. There's a delta H table that we use in this class, and also in 1A. There's also delta S and delta G, which you don't use until you get to 1B. But if you look in the back of most books, there's these what are referred to as thermodynamic values, where you typically will find tables. You'll find what is referred to sometimes as the delta H of F. That's the delta H of formation. And basically what you would do is you would go to that table and you would find all your reactants values and all your product values. So let's just say, for example, here, we have A and we have the delta H from the table is, we'll do minus 22 kilojoules per mole. We'll do B, which is 130 kilojoules per mole, just clearly making up numbers. C is, we'll go negative 35 kilojoules per mole. So you would go to this table, and if you ever have to go to this table, it's really important to make sure you do two things. You want to make sure that you find what you're looking for, but it's more important that you also want to make sure you find it in the correct state. So You can find things in there that could be aqueous, things that could be gases, solids, whatever it may be. You want to make sure that when you go to the table, you just don't find the formula for whatever you're looking for, but it needs to be in the exact same state. So if there's a G next to it in the formula, that means it's in the gas state. You want to make sure you look up the gas value. If it's AQ, it means aqueous. You would look up the aqueous value for it. The other thing is those are per mole, kilojoules per mole. And when we look at a balanced equation, these numbers here, the coefficients, they are sometimes referred to as the moles of each of those things. So when we were to calculate this in my made up example here, we would go to this table. And by the way, you will always find in this table values can be zero. And those are things that are just by themselves naturally, like oxygen gas, nitrogen gas, anything that is not combined with anything else, just an element by itself, how it naturally comes, the delta H value will be zero. So if you go to the table, we'll see some that are zeros as well. So we're going to do our delta H of our reaction. So we're going to take all of our products. So in this case, our products is C. We would go look up our value for C. We do have to multiply the value we find in the table by the coefficient. So the coefficient here is 3. So we got to take 3 times minus 35 kilojoules per mole. And that is all of our products, basically. We're then going to subtract what we get from all of our reactants. So here we would then go to the table and look up A. The coefficient is 2. So we would take 2 times the value of A we see in the table. We would then add it to our other reactant. Now, if there is nothing written in front of here, it is assumed to be 1. So it's assumed to be 1. We typically don't write 1 a lot in chemistry. And we would take basically 1 times the value of B, which is 130 kilojoules per mole. And now we're going to see what we get here with my made up numbers, see how we did. So we're going to take 3 times minus 35. We're going to subtract it from 2 times negative 22 plus 1 times 130, looks like. That's going to give me an error. No, that's going to give me a negative, I believe, 191 kilojoules in this case when I do that. Hopefully, I'm going to give it one more time since it got me an error on my calculator there. Let's try this one more time. 2 times negative 22 plus 130. Yep. Now, when I get this value, you may be asking what happened to the moles. Once again, these are technically moles, so that's how the moles sort of cancel out when you multiply them. Would this reaction be endothermic or exothermic? It would be exothermic, and the only thing that I really have to look at to know that is I ended up with a negative number here. Because I ended up with a negative delta H, it's going to be a exothermic reaction. Any questions on that there? So obviously the table will be provided for you, or the numbers will be provided for you, but that's the important thing. You want to make sure, obviously, you look up the correct state, and you also got to make sure you multiply by the coefficients, add up all your products, which is, again, your final state, minus all your reactants, which is your initial state, and again, that's your state function, right? Final minus initial, products minus reactants in the case of a chemical reaction. Any questions on that? Say again? How do I know? I'm sorry. Say again? That's
Because you put like the equivalent of 3C minus 2A plus the 1B equation.
right. It's always products minus reactants. So this is our equation. So that's our products, right? And then all these guys are our reactants. So whenever you do this calculation, you always basically take everybody on the right-hand side of the arrow minus everybody on the left-hand side of the arrow. And that's, again, your products minus reactants. And again, that's like your final state minus your initial state. No, this is your reactants on this side. So reactants on the left-hand side of the arrow, products on the right-hand side of the arrow, yeah. So you do products minus reactants. So that's why we did products minus reactants here. which is our right-hand side minus left-hand side. Yeah. All right, so let's take a look at one maybe here with real numbers and values. So why don't you calculate the delta H for this reaction, determine is it exothermic or endothermic. These values here on the bottom there is what you would find like in a table if you went and looked them up. And again, that's what the delta H of F is the formation, and that's the table values there. So give it a go, see what you come up with. Reactants, your starting material, right-hand side is your products. And again, to calculate the delta H of a reaction, you're going to take the delta H of your products minus the delta H of your reactants. So on our product side here, we have a couple of things. So we got 2, so we are going to take the coefficient, and we do want to look up the value of NaOH, which is minus 470 kilojoules per mole. We're going to add it to our other reactant, which is H2. The coefficient is 1, so that'll be 1 times our value for H2, which is 0. That's not too bad there. And that basically takes care of all of our products there. Yeah. Any questions on that? We're basically going to do the same thing for our reactants. So we're going to subtract it from our reactant side. So we have 2 of the sodium. So 2 times the value we find in the table for sodium, which is 0. Plus our other reactant here, we have 2 waters. Water, I think, as I was talking about in terms of the state, is probably the biggest one people screw up on. They just find the first water that they see in the table. But water could be in the liquid state. Obviously, water could be in the solid state like ice, and water could be in the gas state like steam. So make sure, it's a very common one. People screw up on this, kind of find the first one in the table, and it may not be the one they need. Here in the table, 286 negative kilojoules per mole. And now we're just going to add it up. And again, this is all of our reactants on this side. So we're going to take 2 times negative 470. We're going to then subtract it from basically 2 times negative 286, as obviously the other one is 0. And that's going to give us a negative 368 kilojoules as our delta H for this reaction. First off, any question on the calculation? Is this endothermic or exothermic? It is exothermic. Again, negative value here for delta H. Exothermic. Negative value, yeah. Any questions on that one there? All right, let's try another one here and see. Maybe. Let me do this one. All right, calculate the delta H for this reaction. Let's take a look. So once again, left-hand side of the arrow, reactants. Right-hand side of the arrow, products, right? So once again, to calculate the delta H reaction, you would go to a table if it wasn't provided for you. And again, going to take your delta H of all your products added together minus delta H of all your reactants. So we'll start on our product side here. We have 12 CO2s. We're going to take 12 times the value of CO2 we see there, which is negative 393.5 kilojoules per mole. We're going to add it to our other product there, which is 6 waters. And 6 times the value of water there, which is negative 286 kilojoules per mole. So this is basically, if you want to think about it, kind of all the energy of our products basically added together. That is, again, our final state. We're going to subtract it from our initial state, which is our reactants. So we got 2 of this guy right there. So 2 times the value from the table, 4904. Plus our other reactant, which is 15 oxygens. Even though there's 15, the value of that's going to be 0 in this case. And that is going to represent basically all of our reactants, right? So our sort of initial state. So again, doing kind of final minus initial. Popping this into our calculator here, 12 times negative 393.5 plus 6 times negative 286 Gonna get us, if we kind of did everybody on this side, negative 64.38, I believe. And we're gonna then subtract that from our bottom, which is basically 2 times 4904. Gonna yield us a negative 65.36. I'll just round a little bit there. Here for our delta H. And once again, we do hit a negative number here, which tells us it is exothermic. Once again, if we ended up with a positive value at the end of this, it would be an endothermic reaction. Yeah. Any questions on delta H, how to calculate delta H? It is, as I mentioned, probably the most common way that, you know, exothermic, endothermic is going to be displayed to you in chemistry, I would think. All right. And as you can see here, delta H for this reaction, minus 890 kilojoules. And once again, that's our reactants higher in energy than our products. Energy has to be given off. This is an endothermic reaction here on the right. Reactants lower in energy than our products. It's going to basically end up with a positive 6.01, telling us it's an endothermic situation in this case. That is basically the melting of ice, right? Which is an endothermic process here. It's going from solid water to liquid water there on top. Let's talk about another important energy value that we come across a lot here in chemistry. These are not negative. That's just from PowerPoint. I'll get rid of both of those there. This is specific heat, and what is sometimes referred to as specific heat capacity. Specific heat capacity is the amount of energy that's required to change the temperature of 1 gram of a substance by 1 degree Celsius. There is a specific heat formula that is used. Q is equal to ms delta T. Q here is heat or energy. It typically has units of joules or calories is the typical units. I would say for us, we probably will see joules most of the time, but it can be calories. It could be kilocalories as well, but typically we will see joules here. M is the mass, and the units here are actually grams. S is the specific heat capacity. Now, I personally use S. Some books will use C as a replacement for that. Some books and places will use SH for specific heat capacity. I personally use S. A lot of people do, but some books will use C, and again, some other books I've seen use SH as well. So any of those three combinations there basically means specific heat capacity. That's really this definition right here. By the way, speaking of specific heat capacity, a number for sure that they want you to know is the specific heat capacity of liquid water. And that's basically liquid water. And it is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. This guy has 3 units associated with it: joules per gram per degree Celsius, or calories per gram per degree Celsius. That is the definition in words. If you read the words, it says the amount of energy, like joules, needed to raise 1 gram of a substance by 1 degree Celsius. So that is why it has all 3 of those units. This is the change in temperature. It is probably the only temperature value in chemistry that you actually leave in Celsius. So it's probably one of the only ones that we actually do leave in Celsius. And that's because typically our specific heat capacity is given to us in degrees Celsius, the temperature. So we kind of keep it. Physics, they roll with Kelvin usually, but here we kind of roll with degrees Celsius in this particular case. So you definitely need to know the specific heat capacity of liquid water. Make sure you know it. It is also that conversion we saw earlier, if you remember, 1 calorie, 4.184 joules. So that is the conversion factor we saw earlier, which you also probably should know. And it's also the specific heat capacity of liquid water. I say it's liquid water because the specific heat capacity of ice or even steam, which is also water, It's more like 2 joules per gram per degree Celsius. So it is different value depending on what it is. Now, when we calculate the delta T, you should always do final temperature minus initial temperature. Why is that really important? It's really important because when you calculate Q at the end here, if you end up with a negative value for Q, as you might imagine, it's going to tell you this is a exothermic process happening. So if you get a negative value for Q, exothermic, to go with your negative delta H. If you end up with a positive value of Q, it is going to be endothermic. So why is the temperature really an important part of the calculation? It is because this number right here, the specific heat capacity, is a positive number. The mass is a positive number. So the only thing that could turn your Q value into a negative number is the change in temperature. So you have to do final minus initial. That will give you the negative if you need it, or give you the positive if you don't. So as we talked about before, right, if something is a exothermic process, if it is exothermic, right, will the person's temperature increase or decrease if they are exothermic? Their final temperature should be decreasing, right? Which means if it's exothermic, when you do the change in temperature, your final temperature is going to be smaller than your original temperature or your initial temperature, which would be larger. And you're going to end up with a negative value for delta T. And that negative is going to turn your Q into a negative value as well, telling you it's exothermic. If it's endothermic, as we've been talking about, it's going to be the opposite. Your temperature should increase, which means when you do your change in temperature, you will have a large number minus a smaller number, and that's going to yield you a positive value for delta T, which will also yield you a positive Q. So sometimes people are taught when they do these type of things to just take the temperature difference. The temperature difference will always be the same temperature difference, but the negative here is actually really important because it is the one that's going to determine whether or not you do actually end up with a negative Q or not. First off, any questions on that there? If I have a large specific heat capacity, does it take more or less energy to change the temperature of that substance? More, right? So water has a pretty high specific heat capacity as opposed to other things. That is why, for example, if we go back to our bathtub example, you got a lot of water molecules in there, which means you need to put a lot of energy in there because of the mass of that water molecules to actually see a big temperature change, as opposed to your cup of coffee, which doesn't have as much mass of water, which means you don't have to put as much energy in there to see a greater temperature change in that 70-degree cup of coffee. Also, why, right, people get a little freaked out when the ocean changes temperature by a very, very small degree. If you just think about how much water is in the ocean and how much energy is needed just to move it a tick in the temperature range, it's a lot of energy. Yeah, so that's what people get a little concerned about sometimes. Any questions on that?